Okay. Then what? Start video. Julian is with us. Yeah, Julian is with us. So is Nicholas, Julian, Brian, Alex, William, Mohammed, and Bryce, and Nathan. We got a good crowd. We've got a good crowd. Oh, it's 11 o'clock. It's time to get started here. Anybody have a question for me before we start? Well, the topic today is more on this polytropic business. So let me write that for you. The topic today is polytropic processes. And then we'll get started on chapter 4. I'd like to spend a few minutes on chapter 4 if we can squeeze it in. Chapter 4 begins the study of control volumes. See, up until now we've been doing control masses, but we're going to be doing control volumes here for a while.
Mr. Griffin?
Yes.
Can you go over the homework problem 3-38?
You want me to go over 338?
Yeah.
I'll be glad to.
Just the PV diagram. I want to see how that.
Okay, why don't I do that? Now, what we're talking about is homework number 9. And homework number 9 is 338 and 397. 397. Now that's due Friday. That's due Friday night.
Would that be homework 10 or 9?
I have 9. Now homework 10, no, homework 10 is chapter 4, number 10, and chapter 4, number 12, and it's due Sunday night at midnight. But I think Mohammed wants me to do 338, and or at least he wants the PV diagram. So let's do that. Sure. Okay, well, let me find it. Let me dig around and find 338. Says here 338. Helium gas expands. And in a polytropic process. And so your PV diagram is going to look like this. And it starts off at 350 K and it expands. I like to put my isotherms in red. So we've got a 350 K right here. This is 350 K. And it's going to get colder. But we don't know what T2 is. I could show you how to find T2. That would be kind of fun. Yeah, that'd be great. While we're at it, now this is T2. It's going to be colder. Now I know it's colder because it's expanding. See, when you compress a gas, it gets hotter. But when you expand, it gets colder. Kind of makes sense. Now it starts off at 350 K and 125 kilopascal. So you're right here, state one. Da-da. And you expand to 100 kilopascals. Well, see, 100 kilopascals, that's smaller than 125. 125 is bigger than 100. So you're right here. And so that's state two. And here you go, there you go. There's your process. And the polytropic constant is 1.667. And I don't want to do any more because Mohammed said that's all he needed was just the, Mohammed, are you happy now?
Yes, I'm happy. That's okay.
Yeah, good. So he's okay now. Let me show you a quick way of getting this T2. Now this is your homework. Some's due Friday, some's due Sunday. It's all in your Blackboard schedule there. You don't need me to write that, but I just thought I'd remind you. Let me show you a nice way to find the T2 here, but I need the room to do it. So we're gonna.
Mr. Griffin, can I ask you a quick question about I don't know if you can see this or not. Is that visible to you? This is my PV diagram. I didn't include, can you see that?
How do I go about seeing? Who am I talking to?
This is Nathan Wallace.
Yeah, Nathan. Now, how do I go about seeing that?
Oh, well, that's okay. I don't know if it's okay. My question is, I don't have, you have two separate isotherms. I did state one and state two and labeled it, but I'm not showing the 350K separate from the T2K. I'm just showing a curve for the state one to state two.
Well, you see, if you just have one isotherm, what you're saying, Nathan, is it's an isothermal process, and it's not. It gets colder. You got to have two isotherms.
I misspoke. I don't mean an isotherm. What do you call a curve there? I'm sorry.
Well, it's the process. Going from 1 to 2 is the process. Now it does have a name, but I haven't explained that to you yet. But it's just the process going from 1 to 2.
Well, I'll just look at the homework grading, and maybe you can let me know what I did wrong.
Oh, okay. Well, here, let me show you this. This is helium. And helium is an ideal gas. We all know that. And so P1V1 is equal to RT1. Ideal gas law. In fact, helium behaves marvelously. It does a great job of behaving like an ideal gas. And we also have P2V2 is equal to RT2. Obviously, because helium is an ideal gas. And then we also have another equation. They said it was a polytropic process, and they even gave us the polytropic constant. So we know P1V1 to the N is equal to P2V2 to the N. We have three different equations there. Here, let me box them up for you. We've got three wonderful equations. Two of them are ideal gas equations, and that third one is the polytropic equation. And what we're going to do is we're going to do a little algebra now. You guys love algebra. And when we get through, we're going to come out with this wonderful equation here. You might want to write that equation down someplace. It's in your book. You could find it. Hope you can read my writing. But see, with that equation, we can get T2. I want to go through the algebra of how to get it, but let's just go ahead and get that T2 here so Mohammed will know what this, or I think Nathan will know what this T2 is. See,
My question was only about the PV diagram, like Mohammed.
yeah, that's fine. But I'm going to get this T2 for both of you guys. Here goes. See, we know T1 is 350. We know P2 is 100. And we know P1 is 125. And we know that the N is 1.667. Hope you can read my writing there. It's a little bit sloppy. Okay, now we're gonna plug that in and get T2. Go ahead. I'll give you a minute. Go ahead and solve for T2, please. Let me ask my friend William. William, unmute and say hi, please. Earth calling William. Come in, William. Having a little trouble here unmuting William. I wonder. There he is. Hey, William. How you doing? William, say hi.
Hi.
Hi. Hey, now, William, did you plug this equation in and get T2?
Yes, I got a 275.8.
That's not what I got. Do it again, William. Take 1.667, subtract 1. That gives you 0.667, and then divide by 1.667. That gives you 0.4. Then take this 100 over 25, or 125, take it to the 0.4 power, multiply by 350.
I got 320.
Yeah, there you go. T2 is, well, you could say 320.1 or just 320 is good enough for me. See, it cooled off. It's 320K. And did anybody else get that? If so, say, uh-huh.
Uh-huh.
Yeah, there's one.
That's what I got.
Yay, good deal. Now let me go through the algebra on this so that you'll know where this miraculous formula came from.
Mr. Griffin?
Yes,
So I got the T2 same, but I used a different equation. So I divide P2 V2 over P1 V1. I got the T2 from here. So is that still okay?
sure, it's perfectly okay.
Okay.
It's perfectly okay. Now let's, but this is a nice way of getting it too.
Yeah,
This is,
I like that
this
too.
is, I like this way of getting it. Here, and let me go through the algebra with you. Now we have equals here and equals here, and when you divide equals by equals, that's going to be equal. The r's cancel out, and what you have is T2 over T1, right there, is equal to P2 V2 over P1 V1. All I did was divide these equations, and here I'm at. Are you with me so far? Can you get to there? Can you get from here to here? Can you make it? Okay. Well, if you think you made it, I didn't mean to smudge that. Now, what I'm going to do is I'm going to take this equation here, and I'm going to write V2 over V1 to the n power is equal to P1 over P2. Actually, I did two algebra steps. Can you get from here, this equation here, to this? Can you make it? Somebody say, uh-huh.
Yes.
Anybody else say, can you make it from here to here?
Yes, sir.
Uh-huh.
Good. Okay, now here's what I'm going to do. I'm going to take both sides to the power of 1 over n. That's legal. And so what you'll have is this here. Can you get from here to here? Can you make it? From here to here, can you make it? I took both sides to the power 1 over n. That just gives you a 1 here on this one, see? Well, I'm hoping you made it. And now what I'm going to do is I'm going to substitute this V2 over V1. And so here's what we got now. We're almost there. We're almost there. Can you get to there? All I did was substitute the V2 over V1 right in there. See what I did? I substituted the V2 over the V1 and just stuck it in there. Okay. If you made it to there, we're almost done. Hey, here's what I'm going to do now. I need a little room. Let me shove this up here so I need that room. I just need the room. I'm going to write this like this. It's just algebra that you guys all know and love. I just kind of took the inverse. See, if you make that a negative, you have to flip them. Are you okay with that?
Yes.
Yay, good going. Okay, now check this out. Can you get from here to here? Can you make it? Because see,
Yes.
you could, yeah, good going. So you could consider this just to the 1 power. And hey, we're done now, because if you go n over n, here's what you'll have. Yay! I tell you, well, here's what we got so far. We got this much of it. There it is. And I showed you step by step how to get there. And I'd take up your valuable time and show you how to get to this one here also. But you don't need me for that. And we're not teaching you algebra. We're teaching you thermodynamics. Do it yourself. But it's a nice little shortcut. But you know, shortcuts can be dangerous. This is a wonderful equation, but it's only good if you have 2 things. You must have an ideal gas, because look, we use the ideal gas law in order to come to it. And then the other thing is it's got to be a polytropic process. If you have an ideal gas, polytropic process, then you can use this lovely shortcut equation. Any other comments or questions? Because I'm going to erase all this and do something else now. Okay, say goodbye to that, but write that down someplace, because it'll come in handy. But be careful with it. It only works for an ideal gas polytropic process. All right, well, let's do a polytropic process with an ideal gas. And this one that I want to do with you is 3188E. I think we need practice with Inglés, Señor. So help me find 3188E. I found it. Helium gas. Hey, we just did a thing with helium gas. It's helium gas, goes from 20 psi. It expands. It's similar to what Mohammed was asking me about, or maybe it was Nathan. Somebody was. 20 psi. See, we're in Inglés, Señor. 600 Rankine. And we're going to go in a polytropic. Hey, that's that same stinking polytropic constant, isn't it? Actually, it's a bunch of 6s forever, but they just rounded off the last one there. And it's going to go to 15 psi. And they said when they started off with 9 cubic feet. And they want the heat transfer. Okay. Well, you know how to do these problems. I've shown you over and over, and we'll just show you over again. Maybe if we show you over and over enough times, it'll soak in. You're supposed to draw the device sketch. Okay, let's do that. And we're going to go 20 psi to 15. You know what? I think we got more pressure to start with. So we'll put a heavy weight on this like that. There you go. There's state 1. See, we got 20 psi. Now at state 2, they take that weight off, and guess what? The piston goes up a ways. That makes sense. It expands. And now you start off at 600 Rankine. It's going to get colder. This is going to be 15 psi. T2. Hey, we just learned a really neat little shortcut equation. Let's use it to get the new temperature, shall we? Here we go. 2 over 600 Rankine. These have to be an absolute. Do not put it in Fahrenheit. You have to use Rankine. Equals P2, which is 15 psi, over P1, which is 20 psi, to the n minus 1 over n. It's 1.6, just like we just did. I want to see if we can do this right. I'm going to shut up, and then I'll call on one of you guys. We have an equation. I know you can do this. Go for it. Let's find T2. Okay, well, I wonder if Reagan, I wonder if Reagan's got that yet. Reagan, did you solve this and get T2 yet?
Yes, I got 534.8.
That's what I got. We now know that it cooled off. And I agree with Reagan, it's 534.8 Rankine. Good going, Reagan. Okay, I think it's time to draw the PV diagram. Isn't that part of the deal? Don't we always do a PV diagram? Well, it's going to look just like the other one. It's helium, and we're expanding. You don't put a vapor dome because this does not condense. It does not change to a liquid. It's an ideal gas. It stays ideal gas. But we can put in 2 isotherms. We can put in a 600. There we go. There's a 600 Rankine isotherm. And then we'll put in a 534. Here we go. This one's a 534.8 Rankine. Do those show up? Yeah, those show up pretty good. Now you start off at 20 psi. Here's state 1 at 20 psi. And we're going to go to state 2, which is at 15 psi. And here's our process. Ta-da, there you got it. Now what they wanted was the heat transfer. Why don't we get the work per mass and the heat per mass? First though, why don't we find the mass? Now they gave us the volume. If you wanted the mass, we can get it. See, mass is equal to the volume over the specific volume. See, they give us the mass. That's it to start with. It changes now. No. They give us the volume. The volume changes. See, the volume gets bigger. The mass doesn't. It stays the same. But see, the volume is 9. We know that. And we can get the specific volume. Here's how we get it. P1 V1 is equal to RT1. Now we know P1. It's 20 psi. We know R. We can look it up. We know T. T is 600 Rang. Hey, we can find V1. I'm going to shut up now for a minute and a half if you need it. Go for it. Find. I want you to find V1. See, we need that to get the mass. We know the volume, but we need this little V1. Okay, get started. See if you can find that. On your mark, get set, go. I don't know if I gave you enough time, but let me ask some people here. Maybe that's enough time. How about Nicholas Sabrata? Nicholas, unmute and say hi.
Hello.
Yeah, hello. Hey, Nicholas, have you figured out this specific volume at state 1 yet?
I got 11,580. I don't think that's correct.
That's not right, Nicholas. What did you use for R, Nicholas?
I got 386 for R.
That's right. Good going. It's 386 foot-pounds force, pound mass, Rankine. You did that right. And what did you use for the T1, Nicholas?
600?
Yeah, I did too. I used 600. Now what did you use for the P1?
20?
That's what I did. Now, Nicholas, did you put a 144 over here on this side of the equation?
Oh, no, I did not. I forgot to.
It's got to be there. I explained that. I'll explain it again if anybody wants me to. But if it's not there, you're not going to get the right answer.
Right, yeah, the volume is in, yeah.
Yeah, the units, see, the units have to be the same. Do that, Nicholas, and tell me what you get for this V1.
80.42.
That's what I got. Now those are cubic feet per pound mass. Now, look at here. Now we know the specific volume. We know the volume. We can get the mass. Okay, I want you to find the mass. I'm picking on Nicholas now. Nicholas, find the mass for me.
Point 11.
Yeah, I get
Pound mass.
0.111. I guess you could round it off to 0.112. What do you think? And what would be the units, Nicholas, for that mass?
Pound mass.
Yes, it's pound mass. Very good. Excellent. Well, we got the mass. We got the specific volume at state one. Hey, look, you could even put that on here. See? This here is 80.42. Is that what we said? 80, yeah, 80.42. And see, these are cubic feet per pound mass. So you can put a lot of information on on a PV diagram. Okay, well, great. We're probably going to need a V2 while we're at it. Now I'll pick on somebody else now. We want to find V2. Now here's the deal. P2V2 is equal to RT2. And we have T2. See, we figured it out. And we have P2. We know that. We know R, thanks to Nicholas. He looked it up for us. And this time, don't forget the 144. And I'll shut up and I want you guys, I'll pick on somebody. I'll pick on somebody. And I want you to find V2. Go for it. You can do this. Find V2. Well, I wonder if anybody got that. Let me go to my friend here, Nathan. Nathan, unmute and tell the gang what you got for the V2, the specific volume at state 2. What'd you get, Nathan?
95.6.
That's what I got. Hey, you know, I'm beginning to suspect we're getting the hang of this. Maybe that's premature, but I can always hope. Well, we've come a long way. We've got a lot of information now. Look here, we've got this one here. V2 is 95.6. Good going. Let's get to work now. Now to do the work, I need some room. Why don't I make some room? Let us make us some room here. Now we cooked up a lovely equation for work for mass. It goes like this. I think I showed you where that equation came from. I think we derived it, in fact. If you don't remember, go back and look at the YouTube video. I don't know whether it was probably last time. I bet it was last time. Now we have all that. Look, we have P2. We have V2. We have P1. We have V1. We got everything. Well, let's do it. What's P2? That's 15 PSI. V2 is 95.6.
I think V2 is wrong.
Okay, well, let me do it again.
I got 10.696 feet.
Now, did you put a 144 in front?
No, I didn't put 144 in front.
Go back and put 144 in front. It won't work without it.
Okay, let me try that. All right, I think we're on the same page now.
Now, is that Reagan?
Yeah, that's Reagan, yeah.
Reagan, you don't get a thank you point, Reagan. I'm sorry. But next time, okay? Next time.
Yeah.
Keep trying.
Yeah.
That's how you have to stick your neck out, and I appreciate you. Okay,
Thank you.
now let's see. We're going to subtract P1. What's P1? 15? No. It's 20. Subtract 20. I'm running out of room over here is the problem. And V1 is, we had it here someplace. Oh, there it is. It's 80.42. And then you divide by 1 minus 1.667. Now, be careful now about the units. Let me talk about these units. See, what we've got here is cubic feet per pound mass times PSI, which is a pound force per square inch. And now here's what we're going to do. We're going to multiply by 144. See, this is English. English is just hard. I'm sorry, but that's the way it is. We're going to multiply by 144 square inches is a square foot. That'll get rid of some of this cubic feet, and it'll leave us with foot pounds. And then we're going to multiply by BTUs by 778.17 foot pounds. That'll get rid of the foot pounds. The inches go away, the foot pounds go away, and you'll have BTUs per pound mass. So see, what I have to do here is I have to multiply this whole thing by 144, and I have to divide by 778.17. I could show you where I got that number if you want. Let me show you where that is. If you go back here in the back and you look under energy, it says a BTU is 778.17 foot pounds. You'll find that in Appendix A. It's in the back of your book under energy. And see, if we do all that, we can get the work per mass in BTUs per pound mass. See, I've worked out the units here for you, but here's the numbers. I want you to put those in for me, please, and we'll get the work per mass. On your mark, get set, go. Do it. Well, I did all that. Let me go to one of my wonderful students here and ask them what they got. Mohammed, unmute and tell us, what did you get for the work per mass, Mohammed? Earth calling Mohammed. Come in, Mohammed.
I'm just getting 177.55, like that. Can you hear me?
Yeah, I can hear you. But that's not what I got, Mohammed. One of us is wrong here. Did anybody get 48.4?
Yeah.
Was that a
That's
yes?
what I got.
Yes.
Yeah.
48. Mohammed, do yours again. I think you just pushed the wrong button somehow. If you go through all this, you'll get 48.4. Now, what those are is BTUs per pound mass. But let me show you guys how a way we could check this. We're going to check it. But to check it, I need some room. How about, I'll just make some room. No problema. We'll just make some room. Now, you know that P2V2 is equal to RT2, right? So we could just go little w is equal to R delta T. Because see, this is RT2 minus RT1. It's just R delta T, isn't it? Divided by 1 minus 1.667. This is actually easier, you know what? And we should get the same answer, right? Well, let's see. What's R? R is, well, we had it on here a little while. It's 386, isn't it? Yeah. R is 386. Now that's, you know what that is? That's foot-pounds force per pound mass Rankine. I wonder if you can read that. It's awful small. I need to write bigger. Now the change in temperature, I can get that. It got smaller. I can almost do that in my head. Is it negative 60? Is it negative 65? I'm trying to subtract these in my head. Do you get the negative 65.2? Did I do that right in my head?
Yes.
Good, excellent. And then divide by 1 minus 1.667. But now, wait a minute. Auga. That'll give you foot-pounds per pound mass. We wanted BTUs per pound mass. So here's what you do. You have to multiply by a BTU is 778.17 foot-pounds force. So take your calculator now. Here, I'll put a little nice circle around this. This is what we're doing right now. You should get the same answer. We're hoping to get 48.4. Do it and see what you get. Well, I got 48.4 something. I got 48.48. No, maybe I rounded off, but you get the same thing. Maybe I rounded off something. I bet I did. But I got 48.4 something. Hey, you could do that if you wanted. You understand? I just use PV equals RT, and it's maybe a little easier. Okay, well, we've come a long way. We've got our work per mass. We know a lot about this problem, but they wanted the heat transfer. Okay, I need some room here, but we can certainly do it. Here goes. And now here's the plan. We got this lovely equation that goes like this. And we just figured out the work per mass. We did it two different ways. And this is what they want. I'll put a little mystery cloud around that. That's what they're after. If we could only get the change in specific internal energy, we could do this problem. Well, we have a lovely equation for that too. It goes like this: C sub V delta T. But we're going to have to look up C sub V in the back for helium. Now the delta T, I think we got that. That's 65.2. Yeah, we got that. So I'm going to let you do that. You can look up the C sub V in the back. You know the delta T, it's negative 65.2. And you know the work, it's, well, it's 48.4. And then you're going to solve for the heat transfer per mass. I'll shut up. I want you to do it and see if you can find the heat transfer per mass. On your mark, get set, go. Well, I did that. Let me call on somebody and see what they got. How about my friend Julian? Julian, unmute and say hi.
Hi. I haven't gotten it yet. Sorry.
That's okay. Take your time. You're going to have to look up this C sub V, Julian. I did that, and it's 0.744. So you go 0.744. Now what that is BTUs per pound mass per degree Rankine. Does that help you any, Julian?
Actually, I think I'm a bit lost. No, sorry.
That's okay. I bet you're not the only one. What we're doing is we're using the first law of thermodynamics. That's what this is. This is our first law. But see, we know what delta U is. It's C sub V delta T. C sub V is this. Delta T is sitting right here. It's minus 65.2 Rankine. So multiply. In the work, we got that. It's the work is right here. It's 48.4 BTUs per pound mass. So we know that. We know all of this. You can solve for the heat transfer per mass. Let me go to my friend Daniel. Daniel, unmute and say hi.
Hello. Sorry.
Hey, Daniel.
I am also
Daniel,
lost.
have you plugged this in and gotten the heat transfer per mass yet?
Not yet. I'm also trying to get caught
That's
up right
okay.
now.
Take your time. Let me pick on Chase. Chase, unmute and say hi. Earth calling Chase. Uh-oh, coffee break. Bryce, you're not going to let me down, Bryce. Unmute and say hi.
Hello.
Yeah. Hey, Bryce, have you plugged in this equation right here where C sub V is 0.744, and we know delta T, it's minus 65.2, and we know W, it's 48.4. Bryce, what'd you get for your heat transfer per mass?
I got negative 0.13 BDUs per LBM.
How come I got negative 0.108 something? Do yours again.
I can do mine again.
Okay, that's what I just got. Negative 0.1088.
Yeah, that's what I got.
That's also what I got.
Yay. Bryce, you probably pushed the wrong button somehow.
Yeah.
Now, what they ask for, they ask for big Q. See, now big Q is M times little q. Now here's little q. Now these units are BTUs per pound mass. Now it's negative, but you know it's not much. But to get the big Q, you have to multiply by the mass. Now the mass is 0.112. We solved that a long time ago. So we know the mass, we know little q, and here comes big Q. This is what they wanted. I'm getting a negative 0.012 BTUs. That's the answer. Now this particular problem, if you had used, like I told you, that should be what do they call that? The polytropic constant. It's really 1.666 forever, okay? If you'd used that, you would have come out with, instead of a negative 0.0 something, it's just come out to be 0. This is a very special kind of process. I told you about it one day. It's called an adiabat. It's an adiabat. Does anybody remember what an adiabat is? Speak up if you do. How about Braxton? Braxton, do you remember what an adiabat is?
I can't say that I do.
Alex, can you remember what an adiabat is?
Not off the top of my head.
That's okay. That's fine. Well, I told you guys what it was, but let me tell you again. I find you have to repeat stuff in order for it to sink in. It doesn't sink in the first time. Now, an adiabatic process, what that is when the Q is 0. There is no heat transfer. I'll tell you how you could do that is if you put an insulator around your piston cylinder. I don't know, cover it with a sleeping bag, that'll work. Don't sleeping bags try to insulate from the cold? You crawl in there and you're nice, warm, cuddly, even if it's 20 degrees outside. They insulate, see? So it's an adiabat. Now there's 2 ways I know of getting an adiabat. One way is to insulate it. Now air makes an excellent insulator. They put insulation, fiberglass insulation in attics to insulate your house in the wintertime and in the summer. But that fiberglass is mostly air. It's got air pockets trapped in it. That's one way to get an adiabat. And the other way is if your process happens real fast. If you got a very fast process, like in an engine, what do you got, 2,500 RPM? See, well, those pistons are going up and down pretty dang fast. And see, heat transfer takes time. And so if you have a very fast process, then it'll be more likely adiabatic. Well, there I told you about adiabats, and this was an example. And we had a lot of fun there.
Professor, this is Nathan.
Go ahead.
Yeah, this is Nathan. I got a question for you. So I had got a similar number for Q. It was negative 0.0088, and I've double checked it. I'm not sure what I did wrong. I have the same CV number. My change in temperature was 534.8 minus 600. Was that?
Yes. Did we get this change in temperature wrong? Let me do that again. 534.8 minus 600 is, nope, 65.2. Here, let me write it out for you, Nathan.
So my change in U was negative 48.5.
Here, we're gonna write it out. What you have is 0.744 times a negative 65.2 equals Q minus, oh gee, I think I erased it, doggone it. I think it's, was it 48? Does anybody remember? It's 48 point something. What do we have?
It's negative 48.5.
It's not a negative. There is a negative in the equation, but the work was positive. It expanded. Do you remember the piston expanded, didn't it? That's
Oh, I'm sorry.
positive work.
Yeah, I was talking about changing U, my bad. Yeah,
Yeah.
work is fine.
Okay, now go ahead, solve that with me, and I'm gonna do it. I'm gonna see what I get here. Well, you know what I get? I get negative 0.008 something.
Yeah, that's what I was getting.
You did everything beautifully. It should come out exactly 0 if you don't round anything off. Now, one of us, somebody along the way rounded something off. Do not worry about it. We did great. Anybody else?
Mr. Griffin.
Yes.
So I was using a different work equation. Like I was not using the small w, I used the big W. And the formula I was getting work with that 5.43 BTU.
What different work equation was it that you
I was
used?
using the big W equals M R delta T n minus 1.
Let me write that down so I can figure out what
Yes.
you did. You're saying big W, Mohammed,
Yes,
equals M
mass
R
delta
T
T n minus 1.
to the n minus 1
No, divided by n minus 1, not the power.
divided by n minus 1.
Yes. And by using this equation, I was getting work of 5.43 BTU.
Isn't it 1 minus n? Isn't it 1 minus n? It's 1 minus n.
It's going to be the same. Yeah, but you can do 1 minus n. That's fine.
Okay. Now the mass was 0.112, right?
Yes.
And R is
386.
386.
Mm-hmm.
And delta T is, oh gee, I erased it. It was at minus 65.2.
Yes.
And you divide by 1 minus 1.666667.
Yes.
That's what you did, right?
Yes, that's what I did.
Well, let me do that. Now don't forget.
Yeah,
you
divide
have
by
to
the 778.17.
Yeah, we're forgetting to divide by 778.17.
Yes.
And you get 5.43.
Yes, that's what I got.
What did we get when we did it?
We got the work of 48.48 BTU.
How much did we get? 48.4?
8 BTU.
Yeah, but we got little w, and if you times little w by the mass, you get your number, Mohammed. It's kind of like big Q is equal to M little q.
There we go. Big W should equal the mass, which is 0.112, times little w, which was it 48.2? Is that what it was? I don't
Correct.
remember.
Or it's
Okay,
48.4.
Now, if you do that, let's see what you get. Well, you get 5.39. I think that's a different, Mohammed. It's just that it's a different. See, big W is equal to M times little w. You okay now?
Yeah, so either way, if we use that work equation or the small w, so answer is gonna be different, but still it's okay.
Well, now here's what you have to do. If you go with delta big U equals big Q minus big W, that's okay. Or you can go delta little u equals little q minus little w. That's okay. But what you can't do is mix them the wrong way. Maybe have some of them big and some of them little. You can't do that. Either go big or little. Stick with that.
Okay.
Okay, we have just enough time to introduce our chapter 4. And I was going to work a problem in chapter 4. Say goodbye to this. We had a lot of fun with that. It was English, and English is just tricky. You know that? It's kind of hard to work with the BTUs and the 144s and all that stuff. But chapter 4 is dealing with control volumes, and it starts off with mass flow rates. And what you have is mass coming in. The symbol is m dot. What it is it's the amount of mass that you have coming in divided by the time that it takes to come in. That's what mass flow rate is. Now there's an equation for it. It goes like this. Where A is your volume or your area, V is your velocity, and little v is your specific volume. Let's look at the units. This is kilograms per second. That's what mass flow rate is. Area, you have cross-sectional area like a pipe. That's square meters. Velocity is meters per second. And specific volume is cubic meters per kilogram. Now, if you work through those units, you'll see that they come out to be kilograms per second. All right, I'd like to do problem 414. We have 5 minutes, and I think we can just barely do it. This is problem 414. It's using this mass flow rate equation. Let me see if I can find it here. Yeah. 6.6 meter diameter household fan takes air at 98 kilopascals. That's approximately atmospheric pressure, and 20 degrees Celsius, and delivers it See, it comes into the fan. That's coming in. Air's coming in. Going out, it goes out of the fan at 105 kilopascals, 20.4 degrees Celsius. Goes out a little warmer, not much, a little bit more pressure. And the velocity it goes out is 1.5 meters a second. What's the mass flow rate? Inlet velocity, outgoing volume flow rate. Well, I'll try to show you. We have our equation here for mass flow rate. So the mass flow rate is the area, which is, well, we need the area. Now, just a minute, I got lost. 0.6 meters diameter. So that would be pi over 4, 0.6 meters diameter squared. That's the area. Now the velocity is 1.5 meter per second. But to get the specific volume, you're going to have to go PV equals RT. Now we know the T, only you have to use Kelvin. So that would be 293.15 Kelvin, and R is 0.287. P is 98 coming in. So see, you can get the specific volume from here. Let me go ahead and get it. Okay, I got the specific volume. I'm getting 0.85 cubic meters per kilogram. Now all we got to do is plug that in. We have 3 minutes left. Plug that in. You have 1 minute to do that for me, and I'll tell you what I get for the mass flow rate. Go for it. Now wait a minute, I did something wrong. Just 1 tiny minute here. If you read the problem, that 1.5 is the exit velocity. We need the exit. I'm doing the entrance. Now that would be the same. The area of the fan, that doesn't change any, but the exit velocity is, that is the 1.5. I did that right. That's the exit velocity. But this here, we need the exit specific volume, and see, that's wrong. This should be 105. And this should be, would it be 0.55? I think so. I think that's right. It'd be 0.55. Get that right? Yeah. Yeah, I did that right. Okay. Oh, we only have 2 minutes left. Okay, now this is wrong, in other words, because what I did was the incoming, and I'm putting in the numbers for the exiting, going out. Okay, here goes. I'm getting a slightly different number, not much. And so now we can get the mass flow rate. Okay, here goes. We're gonna get the mass flow rate now. Well, I got an answer. And I'm getting a mass flow rate of 0.5286 kilograms per second. That's the correct answer. Well, I wish I had more time with you, but we'll get back on Tuesday at 11 for more fun. And you have time to do that homework. I gave you some homework there, but I bet you can do it. Okay, here's your last chance to say anything because I'm going to sign us off. We're going to say goodbye.
Thank you.
Bye-bye,
Thank you.
students.
Have a good
See
day,
you
Mr.
next
Griffin.
time. Thank you.